Hi everyone, in this video I'm going to teach you a little bit about circle geometry. So let's say here's a circle, and for the purpose of this example I've indicated the center of the circle here, this little red dot, and I just want to go over a few terms that you probably are already familiar with and maybe a few more that you aren't. So if this is the center of the circle here, I can draw a line from the center anywhere to the circle, and you know that that's the radius of the circle. Okay, so from there to there, from the center to the circle, that distance is known as the radius. If, on the other hand, I go all the way across, like so, and I'm still passing through the center, that is known as the diameter. So that immediately brings one relationship, in that the diameter equals 2 times the radius. Okay, so that's the first thing. There are a couple other lines on a circle that are kind of interesting. One of them is if you take any 2 points on a circle, like here and here, for example, and you join those up with a straight line, that's called a chord. It's the same word as you might remember, as you might have heard in music class. There's nothing in particular special about a chord, at least not on its own, but there are some interesting things when you start looking at perpendicular bisectors of chords. They have some pretty interesting properties, and I'll ask you a question about that in class. There's one other line segment, one other line that's kind of interesting on a circle, and that's called a tangent. So a tangent is a line which just touches one point on the circle. So it just kisses the circle right there, and that's called a tangent line. Okay? So all those lines have to do with circles, and in principle we'll spend most of our time talking about the usual ones, the radius and the diameter. I guess there are a few other things that you might remember about circles. For example, you might remember that the circumference, which is a special word for the perimeter of a circle, is equal to pi times the diameter, and the area of a circle is equal to pi times the radius squared. Okay, so those are typical things that you might want to calculate when we're doing stuff with circles. Okay, now if I take this circle and I place it onto a Cartesian xy axis, then what I really want to do at this point is I want to come up with a relation that allows me to graph it. So I hope without too much trouble you'll look at this and realize that the radius of my circle here is 4 units. So if I start at the center and go to this point here, you can see that I've gone 4 units. And if I go up, it's 4 units, down 4 units, and so on and so forth. So the radius here is 4. But setting that aside for the moment, let's pretend that I didn't notice that. Then what I can do is I can imagine a point. Let's say this point here. I'm trying to choose one that's not a nice point. And that point is x, y. And I can always draw, oh geez, that's not very good. I can always draw a straight line. Still not very good. Let's try again. There we go. I can always draw a straight line from the origin to that point, and that line is the radius. Allow me to just zoom in for a second here. Because what I want to do now is I want to construct an altitude from this point down to the x-axis. So that'll make a right angle. This height here will be y. This base will be x, that is the base of the triangle there. And now you see I can apply the Pythagorean Theorem. Specifically, that x squared plus y squared, those are the 2 legs of my triangle, equals to the radius squared. And this relation governs my circle. Okay, so generally speaking, what happens is that x and y will always stay variables, just like they would in the equation of a line or a parabola or something else. Whereas r is the number, it will be a number. So in the case of my radius here, this number would be 4. So for this particular circle, I would have x squared plus y squared equals 4 squared. And just to keep that, just to simplify that a little bit, we would normally write that as 4 squared, we would write that as 16. So that would be the equation of this circle. All right, so how we might use this, we might ask ourselves, how can we show that a particular point lies on a particular circle? So in this case, we're asked to show that the point 3, 4 lies on the circle given here. And so one way to do this is just to do a left side, right side verification. So on the right side, that's just going to equal 25. Pretty simple. On the left side, however, I've got x squared and y squared. And so what I want to do is I want to take the point that I'm given, 3 and 4, substitute 3 in for x and 4 in for y, and work that out. So I'm going to have 3 squared plus 4 squared, and that's going to equal 9 plus 16, which equals 25. So 25 on the left side, 25 on the right side. That works. So that point, 3, 4, does lie on the line. I've verified it. Another example could be something like this, where we're asked to determine the diameter of the circle centered at the origin, 0, 0, that passes through negative 3, 5. So our starting point will always be the equation of a circle centered at the origin, like this. And now I substitute my point in for, again, x and y. So I have negative 3 squared plus 5 squared equals r squared. Work this out. Negative 3 squared is 9 plus 25 equals r squared. Add those together, and I have 34 equals r squared. Since I'm asked for the diameter, I should probably try and figure out r instead of r squared. So in this case, I will say the square root of 34 equals r. A radius is always positive. You can't have a negative radius. And so 2 times that number is my diameter. Okay? I don't have a calculator on me at the moment, but you can work this out. It'll be a number very close to 12. Okay, so that's basically that. We've got a diameter. There are a couple extensions that you can do. So right now, we're going to stick to circles that have their center at the origin, but there's no reason why a circle should be centered at the origin. So in general, a circle can have its center anywhere. And in that case, the equation gets changed to x minus c squared plus y minus d squared equals r squared. So in that case, the center is the point CD. This may look familiar. This sort of thing may look familiar to you here. X minus some number squared. That's actually the same thing as a translation for a parabola, right? In vertex form. So this kind of looks like the vertex of a parabola, and that's that's basically why that is where it is. This might look a little different here, but it means the same thing. So in here, this tells us about a horizontal translation, and this tells us about the vertical translation of the center. You can also do interesting things with ellipses. So an ellipse is what I sometimes think of as a squashed circle, so something that looks maybe like that. Well, that doesn't quite look right. Well, you get the idea. It's also sometimes called an oval. Okay, so an ellipse. So the equation for an ellipse is similar to that of a circle. In the most general form, it looks like this: x minus c squared, let's say over, I need another letter, a plus y minus d squared over b equals r squared. There are actually a few ways of writing the equation of an ellipse. But yeah, depending on the source that you use. Basically what's happening here is that, again, we can move our center just the same way that we did with a circle. And these two numbers, a and b, will affect the shape of the ellipse, whether it will be squashed this way or whether it will be squashed this way, if you can imagine that going on there. Okay, you can play around with, check this out in Desmos to see how this might be used and abused. In general, if you are interested in learning a little bit more about more advanced math, we no longer do this in high school, but this circles and ellipses and parabolas even are all part of a special family of functions called conics. So I know that if you do a little bit of reading online, that's not comics, that's conics with an N. If you do a little bit of reading online, you can learn all about them. They're pretty cool and a nice extension for the things that we learn in grade 10 math. Okay, that's it for today, folks. Thanks very much. I hope you have a nice life, and don't forget to be awesome.